Hi, I'm Claire Vacherot. I'm a security auditor at Orange Cyberdéfense in Lyon, and I love devices and protocols that interact with the physical world. Today I'm going to talk about one of these protocols, KNX, and its implementation over IP, which is mostly used in building management systems. So first, let's briefly introduce what building management systems are. Basically, such systems aim at connecting components in a building to monitor and control them from a central location. This includes, for instance, lighting, shutters, air conditioning, and even access control, safety alert, etc. From a technical point of view, this often means that sensors and actuators that communicate using field bus protocols are now linked to the LAN, sometimes using devices that may be exposed on the internet. From a security point of view, well, this is kind of a disaster, as we connect field bus protocol to the outside world while they have clearly not been designed with cybersecurity concerns in mind. As a result, an attacker with network access to such systems may be able to interrupt or alter a facility's environment. For instance, one could turn on the heat or change the temperature thresholds in a data center or on a production chain with specific temperature requirements and damage equipment or production. Or one could constantly trigger the fire alarm for no reason, and the next time people would hear it, they wouldn't believe anymore that there's a real threat. Or one could turn off the air conditioning in an office, factory, or other closed place where people work or live, degrading the air quality, which may become really dangerous. As you can see, targeting building management systems can have a physical impact on devices and on human safety. So, finally, one can take advantage of exposed devices that are part of a building management system for further attacks, by using them to gain a foothold in a network or to move onto critical networks, areas, and systems. Well, now that we know what we can do, let's focus on one of these protocols and see how we can do it. So let's talk about KNX. This is a common field bus protocol for BMS for both industry and domestic use. Not the most common one, as there is BACnet, but still widely used, especially in Europe. As you can see in this screenshot from Shodan, we can find a lot of devices exposing port 3671, which is the port for KNXnet IP, the protocol specification for KNX over IP. So KNXnet IP allows interfacing from LAN to KNX and vice versa. As you can see in this typical example of network architecture from the KNX specification, it requires a gateway between the IP network and the field bus, referred to as a KNXnet IP server in the standard. Typically, when we want to send a configuration change to a device from the workstation, a KNXnet IP frame will be sent to the server, which translates it to a KNX frame to transmit to targeted devices using a KNX specific address topology. The KNX Association provides a commercial software for configuration called ETS. So I just show you an example, and I use ETS for visualization, and also a very nice tool called KNX Map to change the value of a group of objects. So this is ETS. We can see on my KNX project that I created a group object for alarm objects, which are switch off. My KNX project is linked to a real test device that I will use for this presentation, but for responsible disclosure reason, I won't tell which one it is. So I run KNX map on the test device at this IP, and I want to write to group address 111, so for my alarm objects, the value 1. Now, the value has been changed to 1. Hopefully all the alarms have been triggered. You can see on Wireshark that a lot of KNXnet IP frames were exchanged. For example, this frame is a description request sent by KNXMap to request the server to describe itself. KNXnet IP frames are usually sent over UDP, and the structure of frames is quite complex. The format, order, and the content of blocks and fields in the body change for each type of message that can be carried by a KNXnet IP frame. And there are KNXnet IP specific frames, especially for device discovery and KNXnet IP connection and configuration, and other types of frames that embed raw KNX frames to transmit to devices. So here you may have noticed that I was able to change the value without authenticating in any way. Well, there are a few things to say about KNX cybersecurity. The standard explicitly says that the security of KNX relies on its low exposure, which is a bad idea considering KNXnet IP. Authentication is not mandatory. There are extensions for KNXnet IP frame transport security that manufacturers are free to implement or not. So cybersecurity just looks optional. For instance, my test device for this talk implements authentication, but it's not enabled by default. And apparently this is quite a common setting, and this configuration does not seem to be changed so much. So this means that knowing the IP address of a KNXnet IP server, we can directly send valid KNXnet IP frames to alter the KNXnet IP server and underlying sensors, actuators, and controllers' behavior, using automated tools such as KNXMap, for instance. So please don't do it. However, doing this limits us to running legitimate KNX commands and triggering legitimate functions on devices. Please don't do it. But what if we send malicious frames to a KNXnet IP server? We would then be able to trigger unexpected behavior, gain a privileged access to a device, and so on. So there's a large number of known attacks and vulnerability research projects targeting IoT, industrial, and BMS devices that rely on testing network protocol implementation, often with fuzzing, but I haven't found any targeting KNXnet IP. I think this is because crafting frames that are valid enough not to be rejected by devices and invalid enough to cause unexpected behaviors is quite complex. The KNX standard says it better. It is quite unlikely that legitimate users of a network would have the means to intercept, decipher, and then tamper with the KNXnet IP without excessive study of the KNX specifications. Yeah, indeed. That's why we decided to write a Python-free library that does not necessarily require this excessive study of the KNX specification to interact with KNXnet IP servers and underlying KNX devices. It's called BOF, for Boîte Opener Framework, and it can be used to craft, alter, and parse frames from supported protocol while sticking to the specification, which is a very important part. It's available on Orange Cyberdéfense GitHub page, and you are free to use it carefully and to contribute if you want. So how does this work? We thought of 3 different type of use, depending on the user's level of knowledge about the protocol and the specifications. First, the basic usage, which requires no knowledge about the protocol. So you first need to import the module, then call the discovery method with a KNX server IP, and then you get some information about the server with a user-friendly formatting. Then the intermediate usage, requiring knowledge about the protocol, but not about the specification. For instance, knowing what type of frames are exchanged, but not necessarily the content of these frames. So let's do the exact same request as in the previous example, but instead we clearly specify the different steps we take. First we connect to the server, then we create the frame and specify the type of frame to send to the server, which is a description request here. If we print the object, we will see some details about its structure. We add some information in fields, here the source IP address and port, which are stored in the connection object. Then we send the frame and expect a response from the server. Here we go. The response contains the description we asked for, and we can access interesting fields directly. Actually, this code is very close to the actual discovery function code, as a higher level function in both are implemented using lower level ones. And the last use case allows full control over frames and requires knowledge about the specification. This is, of course, to me the most interesting part of both. We'll talk more about it in the remainder of this presentation, but here is a quick example. So here we have another rewriting of the discovery function, except that we really write it from scratch. We can create and modify blocks and fields specifying their names, length, and content, and then add it to the final frame. We could also remove blocks and fields, change their order, length, content, and so on. Just to say a few things about the code, when we receive or create a frame to send as a byte array, every part of the frame is represented as objects. Frame objects embed block objects, which are containers for other block objects defined by the KNX specification, or directly containers for field objects, or both. Field objects are the smallest part of the frame, and they have a name to refer to them in the code, in the scripts, a size in number of bytes, and a value as a byte array. These classes are generic, as we decided that both codes should not be bound to a protocol so that we can add more. So protocol-specific content is written to an external JSON file containing details about the existing frames, block types with a predefined set of fields, type codes, etc., as defined in the KNX specifications. Objects in both are dynamically created and filled with attributes according to this file. And for now, the KNXnet IP JSON file includes some frame and identifiers. However, the specifications are really big and complicated, so there is still a lot of content to add. So let's try to do the right operation we did in the beginning of this video with both. To do so, we need to establish a tunneling connection to the group address and write the value. Here is the code to build the write request. We define the predefined format of the frame and then fill in the fields with the appropriate values. We then send the request and wait for the acknowledgement. Here. This is it. What we first wanted to do with both was to write a KNXnet IP frame fuzzer to test KNXnet IP servers. To do so, we used both to create and send invalid frames to a test server to trigger unexpected behaviors that we want to investigate, to hopefully discover exploitable vulnerabilities. So let's do it. For this first try, we focused on fuzzing one type of frame that carried read and write orders interpreted or relayed by the KNXnet IP server to the KNX bus. Such orders are sent as medium-independent KNX data embedded in some frames as a special block called KEMI for a Common External Message Interface. The first step is to generate inputs following the format of a valid frame that include a KEMI block. So our valid base frames look like this. which is to mutate only the chemi blocks fields in order to trigger unexpected behaviors. As a chemi message is different for each type of order, we decided to focus on property request messages. And noted that we could have started damaging things if we chose to test the property write request message instead. Now for the mutation. KNXnet IP servers are very strict regarding the frame's format and are very likely to reject any frame that does not match what they expect. That's why when we mutate our frame, we need to closely stick to the format defined in the specification to make sure that the server interprets it. So to begin with, we can mutate our frame by writing a random value to a single random field in the chemi block, and later restrict the mutation to fields or values that triggered unexpected behaviors. Here we exclude the message code field because it has to be valid for the server to accept it. So, our mutation function starts from our valid frame, randomly chooses a field from the chemi block except for the message code field, and then writes a random value to that field, matching the field size. We return the mutated frame, switch back to the original frame, and repeat. Each frame is sent to our target, but for each one of them we need to follow a specific exchange sequence that you can see here. We first connect, send a configuration request, wait for the acknowledgement and response, acknowledge back, and disconnect. Depending on how the server responds or not, we will know if something unusual happened. We may have one of these outcomes. 1. Everything worked fine. The exchange occurred as expected. 2. We received an ACK frame but with an error code, meaning that the request was processed but an error was handled by the server. 3. The server stops responding, times out. 4. The server ignores the frame as it is invalid, but in our case we assume that our frame is valid and will not be rejected by the server, so this would be an anomaly. So we're interested in behaviors 2 and 3, so we want to store for further investigation frames that were processed but either triggered known errors on the server or, even more interesting, frames that crashed the server. This is the final code. I just scrolled quickly through it so you can see, but you can also find it on both GitHub repository. So we can see that we have our mutation function, the first function which will reproduce the frame exchange and detect the different behaviors. We store the details about the frame that triggered the behavior in a file for further investigation, of course. So let's run it on my test device and wait for something interesting to happen. I just cheat a little and now we have a few results. So I already ran it for quite a while and I currently have more than 30 frames to investigate. Unfortunately, I thought I would have the time to start looking at them between the submission of the paper and this talk, but I didn't. So I guess that if I find something interesting, I'll have to do another talk next year. So see you then, and thank you all for listening. Bye. Hi.
Hi. So I have a few questions from the IRC. First, why would someone ever want to connect KNXnet to an IP network?
Because of Internet of Things, I guess. People tend to want to connect these kind of things for instance, for home automation, for to control from one central point the whole building features, I'd like to say, such as shutters. So you use your smartphone from one central location to just shut down everything, or you just or in industries they are used to control the power consumption for financial reasons, for instance, or for air quality measurements, to trigger alerts, to send automated messages and perform automated operations when something is wrong or so.
Okay, and where can those devices be found? Where are they used, and how widely?
Just like I said, for home automation, so for domestic use, for industries, in offices, now in a lot of open spaces, just lights are automated, shutters are automated, air conditioning is automated too, and this is often KNX or BACnet, which are used in those cases.
So basically everywhere, and it's connected to the internet. That's nice to know. There's a question. The protocol, the KNX protocol, has it been implemented in SCAPE 3K?
Not yet. This is something that would be a really cool thing to do. So I don't know, maybe I start doing something when I have the time to do it. So, and of course, if people are willing to dive into KNX, this is a really big problem, I like to say. But if someone wants to, I think KNXnet IP in SCAPI would be a really good thing.
Okay. From Zoom, do you think the BOF and exploitation is close?
The
BOF, the
yeah,
framework
both.
of exploitation.
Yeah.
Both. Sorry.
Sorry. Is what? Sorry, I didn't.
Close to the exploitation. How easy is it to go from one to the other?
There's a lot of things left to do. Yeah, one can do the main thing, but I think if it's now you can do the basic operation, but if you want to go to do the whole process of interaction with such devices, there are still things to do.
Okay. Did you think to attack physically the devices to have an easy feedback?
Yeah, but that's well, there are many things to do. So I have to do it next, I think.
Okay. Thank you. I think that's
You're welcome.
all. No more questions, is there? No. Well, thank you very much for a talk. Very interesting.
Thank you.